All right, last time we added recursion to our language, and it was quite easy to do that. We just added this new identifier attached to lambdas, and then included that in the closure environment when we created it. And we mainly added recursion because we saw inside the lambda calculus that we could get recursion, and now we just decided to make it convenient. So today what we're going to do is we're going to extend our language with data structures. And the idea of extending with data structures is that we have also observed those things to be useful inside of in normal programs, and justified because the lambda calculus already includes them, so we're going to add them too. We're going to add data structures of a kind called algebraic data types. Algebraic data types. The idea behind algebraic data types is to understand that a very small algebra of different kinds of structures will allow us to write down any different kind of data that we care about. So we're going to say that a data type is either what's called unit, which is a data type with no interesting components. This is basically like void in C. Or it is a pair of two data types. This is a pair. Or it is a variant, an either. So this is called, what do they call this? It's called a sum / variant. Okay. So let's look at some examples of what these means. So unit means something with no interesting pieces of it, so there's no internal components. And a pair is obviously one thing and something else, so think of like a position, like a Cartesian point. Now sums are a little bit more interesting. Sums basically say you know whether or not something is the thing on the left or the thing on the right. Let's look at a few example data structures written in this way. So first of all, think about a Boolean. A Boolean can be represented as 1 plus 1. The idea here is that this value is, say, false, and this value is true, and they don't have any internal pieces to them. All that's important is that you can tell which one is which. Another example would be like a natural number. A natural number is either 1, meaning something with no interesting information, so in this case 0, or it's another natural number. Now, of course, because this natural number right here is on the right, we know that it's on the right. Therefore, this right here is a unary encoding of numbers. We could also represent numbers in binary by saying it's either a string that's empty, or a string that has a 0 in front of it, or a string that has a 1 in front of it. And so this right here means 0, this right here means the successor. This would mean epsilon, and this would mean a 1 and then some string, and this would mean a 0 and then some string. Okay, then you can think about something like a list. Imagine that we had a list of something, we'll call A, and that would be either the empty list, or it would be a pair of an A paired up with another list of A's. This right here would be like a linked list cons node. What about a binary tree? A binary tree of A's would be either an empty node or an A paired up with a binary tree of A's and another binary tree of A's. I wrote T, but I meant to say A. Binary tree of A's. Okay, so a large number of data structures can be represented this way. Now we can write these things down. Well, we can encode them into our language by making the following changes to our language. We're going to go from J4 to J5. And we're actually going to add a significant number of things. Our expressions are going to have the following form. We're going to have variables, values, applications, ifs. Okay, this is all the same as before, and now we're going to add one new thing. And the purpose of this new thing is to be able to look at a variant and determine whether we're on the left-hand side or the right-hand side. So we write this as case E of in left x goes to E, or in right x goes to E. Actually, let me write it as or. So of or. Okay, so the idea here is that what case does is it consumes these variant objects. Now what values are as before, numbers, bools, primitives, and lambdas. So this is all as before. But now there's a few new things. There's a new one that's called unit, and that's the unit value. There's also a pair of values. There's also an in left of a value and an in right of a value. And primitives include all the same stuff that we had before, plus there is a pair operation, an in left operation, an in right operation, a first, and a second. Okay. All right. So now let's look at what these things mean. So we're going to have the following rules. E of first pair of uv is going to be equal to E of u, while E of second pair uv is going to be equal to E of v. Hopefully this makes sense. The next one is slightly more complicated, and this has to do with cases. So how do cases work? So we'll say that E of case in left V of in left X arrow EL, or in right, let's call this XL and XR, arrow ER, that is going to be equal to E of EL, that's this one, where we find all the XLs and replace them with V. Then there's a similar rule for when you call case on an in right. When you call it on an in right, rather than evaluating the EL block of code, we're going to evaluate the ER block of code. And we're going to find the XR and replace that with V. All right? Now, I'm not going to provide you with the changes that you should make to your CEK machine. Consider this a test of how you can look at these rules and derive what the CEK machine should do. I'm going to give you some advice, though. So my advice is that you should make it so that, pair, first, second, all those things should just be primitives that know exactly what the representation of pair values is. In left and in R are also just primitives that know how to construct the right kind of thing. But case actually needs to be part of your CK machine rules, and so you're going to add a new rule that handles when there's a case. And the reason it needs to do that is because it introduces names, therefore it modifies the environment. Okay. The next thing that I want to do is let's show how using these new features we can expand the things that our language can do to do list manipulation. Because of course many programs deal with lists, and that's very useful. So a list is either empty or it is cons, i.e. a node, with a thing and then another list. So what we need to do is we need to write down a representation for empties and a representation for conses. So we can do it this way. We can say that empty is just a left of a unit. And cons would be a function that takes the data and then the rest. And what it would do is it would have an in right of a pair of the data and the rest. By the way, what I'm writing right down right now, we're going to call that your standard library. So you should make it so that inside of your implementation, anytime someone writes a program, they automatically include this code and whatever their program is, and then they can use all of these functions. So let's write some example functions on lists. We could write a function like length. Actually, hold on. Yeah, we'll write this one. We'll write a function like length. And what length does, it's going to be a recursive function that's going to take as an argument an L. And what it'll do is it'll say case L of in left goes to 0, because if it's an in left, then that means it's an empty. And if it's an in right, that means that there's a pair. And we'll do 1 plus calling ourselves recursively on the second thing inside of that pair, which is the rest. Okay. We can also write a function like map that's going to be lambda rec. It has a function and then an L. And what we're going to do there is we're going to say case L of in left goes to just L, because if we get called with the empty list, then we'll just return the empty list. But if we get called with a cons, then what we'll do is we'll construct a new cons that comes out of calling the function f on the first thing inside of the pair, and then calling ourselves recursively with the same function and the second thing inside of the pair. We can write the function reduce. What reduce does is it will be called with a function f, a value z, and then a list. And what it's going to do is it's going to say case L of, so it's right up here, in left goes to just the z value, and in right of p is going to go to calling ourselves recursively with f, and then f called on z and the first thing in p, and the second thing in p. An example use of reduce would be something like this. We could call reduce with a function that takes in x and y and adds them together. The z value would be 0. And then we could call it with the list cons 1, cons 2, cons 3, empty, close, 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 and that's going to be equal to 6. And it's going to be equal to 6 because the 1 we're going to call f with 0 and 1, and that's going to return 1. Then we're going to call f with 2 and 1 and get 3, and then we're going to call it with 3 and 3 and get 6, which is the answer 6. Okay. The next thing that you could do is, you should do, is we can add something to our language that's kind of like object-oriented programming. So imagine that we want to do object-oriented programming like this. So we'll extend our language of E with the form object with curly braces and then x a colon E, and there can be many of those. And then there will also be a form called E.x. And values would be extended with objects, which would have an x and a v. And then the rule would say something like E of object x 0 v0 dot 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 xn vn dot xi is equal to E of vi. Okay? So now, how could we implement this? Well, what you could do is we could create a value in our standard library called empty percent. And why is it percent? Because it's object oriented. That was just the empty list. Then we could write a function called set that takes in an object, a variable, a variable name, and then an expression. And then what we could do is turn that into cons of pair of that variable name as a string, and then E, and pair that up with O. Then we could take something like object of nothing and turn that into empty. Object of x0, e0, and then xm, em, and turn that into set object of xm, em to x0, e0. Okay. Then, anytime you wrote anytime you wrote, whoops, wish I could change it so that's the default. E.x, we could turn that into a function called lookup that takes E and looks up the string x. Now notice that we don't have strings in our language, so you could add those. You'd add those, and they would be like these key things. Okay. So what is this lookup function? Lookup is a function that you could write. So lookup would be a recursive function that takes in a list and a key, and what it's going to do is it's going to say case. Actually, I guess it takes an object of in left, so it ever got empty, then it would error. Okay, and if we ever got in right of a p, then what we would do is we'd say if, and we call some function like string equals k and the first thing inside of p. If it's equal, then we would return the second thing inside of p. Otherwise, we would return lookup, we would call rec. We would call rec on the second thing. Not the first p. We would want the first p. And here we would want the second of the first p. And then this would be the actual second p. And we got to call rec also on k. All right? So what this does is it represents objects as lists of their attributes. And these things right here, you could put, set and empty and lookup in your standard library, and then you could put the object and the e.x, you'd put those in your desugarer, And now your language knows about objects without having you actually have to implement anything yourself. There's lots and lots of functions that it's now possible for you to write, given what there's lots of things that you can write now. So I mean, you can write functions like, you could like filter lists, for instance. We could write a filter function. So filter is going to take a predicate and a list, and what we're going to do is we're going to say case L of in left. We're just going to return the list, and if it's an in right, let's call this PR for predicate. Then what we're going to do is we're going to say if the predicate passes on the first thing in P, then we're going to do a cons of the first thing in P, and then let's call it R prime. Otherwise, we're going to turn R prime. R prime, where we'll say let R prime equal calling rec. Keep writing the name of the thing instead of rec. Calling rec on the predicate and the second thing in P. And so this is a little filter function. So we can do length, we can do filter, we could write append to append two lists together. So lambda rec xy, where we'll say case x of in left just goes to y, and then in right P goes to a cons of the first thing in P, and then calling rec on the second thing in P, and then y. Okay, so there's tons and tons of things you can write. Our language is extremely powerful right now. Okay. So, what's next? So I guess the next thing that we'll do is end this lecture and move on to the next one. So see you all in a little bit.